Chapter 7, Dimensional Analysis and Modeling. Okay, class, let's imagine we are playing with toy blocks. You have blocks of different colors and sizes, and you are trying to build a big tower. But before you start stacking, you count how tall and wide the blocks are. This is just like what we do in engineering when we talk about dimensions and units. Dimensions are like the basic idea of what we are measuring. Things like length, time, and weight. Units are just the names we give when we measure them, like meters, seconds, and kilograms. It's important because when we make calculations, we must be sure we are adding and multiplying the same kind of things, just like you wouldn't mix apples and oranges. Now, let's imagine you were playing with a water gun. You pump it, and water shoots out. You notice that the more you pump, the farther the water goes. This is because of energy changing from one form to another. In fluids, we have something called the Bernoulli equation that tells us how pressure, speed, and height are connected. All parts of the equation must be speaking the same language, meaning they must have the same dimensions. This rule is called dimensional heterogeneity, like making sure we don't accidentally add apples and bananas in math class. Sometimes we have very big things like ships or airplanes, and we want to test them without spending too much money. What do? We make small models. But to be sure that what happens to the small model also happens to the real thing, we must follow three simple rules. First, the small model must look the same as the big one. This is geometric similarity. Second, how the water or air moves around must look the same. This is kinematic similarity. Third, the forces pushing and pulling must act the same way. This is dynamic similarity. When we get all three, we can learn a lot from small models. Let's say you are testing a toy car in a wind tunnel. You blow air on it and see how much it pushes back. To make sure it behaves like a real car, we use something called dimensionless numbers. These are special numbers with no units, like the Reynolds number or Froude number. They help us check if the small toy car is feeling the same pushes and pulls as the big real car. It's like playing with Lego cars, but pretending it's a real race car. When engineers don't know all the complicated math equations, we can still be smart using something called dimensional analysis. We write down everything that matters, like length, speed, time, and see how they are connected. Using the Buckingham Pi Theorem, we mix and match until we find special dimensionless numbers called pi terms that tell us what really controls the problem. It's like solving a puzzle by only using the shapes of pieces without reading the instruction book. In the end, this way of thinking saves engineers time, money, and effort. Instead of running hundreds of experiments, we can just test a few and use the pi numbers to guess the rest. That's how we make airplanes safer, ships faster, and cars smoother. Just like building your tallest tower or fastest Lego car, understanding how things scale up or down helps us make better designs without making expensive mistakes.